So, how do we improve our access to deep space exploration? That's the question that the Japanese Space Agency posed to our laboratory at Hokkaido University. And today I'll present to you the nitrous oxide polyethylene hybrid rocket thruster that we're developing to answer that call to deep space. So, here's what we did. First, we narrowed down our envelope to a 550 millimeter cubic microsatellite so we can piggyback on existing Earth launch vehicles. We're aiming for at least a delta V of 1 kilometer per second so we can go from GTO into meaningful interplanetary orbits. We narrowed down our hybrid rocket to use nitrous oxide and polyethylene, and we had to do around 2 years of subscale testing to develop the internal ballistics equations that we need for our design calculations. Now we codified our design in the new MATLAB app designer, so we have a nice interface where we can do parametric analysis. And today I'll show you the results of our nitrous oxide thruster and compare them to what would happen in theory if we use gaseous oxygen as our oxidizer. Now this is in context of Dr. Jens' project at NASA JPL, where they're doing a great design and development of a CubeSat hybrid rocket thruster which uses gaseous oxygen for its high ISP. The last few slides are essentially our current status. So we have a flight design model developed in CAD, and we're moving towards the full-scale, full-duration burns of our motors in a high-altitude chamber which we constructed this summer. I end the presentation with the word share in capital letters. This is an acronym that's a play on words that we're sharing our capability on the existing Earth launch vehicles so that we can access deep space. The problem statement that JAXA was facing was, of 13 H2A launches that went all the way to GTO, only 3 of those went into deep space afterward. And we want this number to be 13 of 13. Now, why would this even come up? Every one of these 13 launches had piggyback capability for microsatellites. For example, this is straight from the manual. 4 microsatellites could fit on a typical H2A underneath the main payload. So, what can we do from GTO if we piggyback the microsatellite there? Well, with 700 meters per sec, you can reach the Earth escape velocity. But with Earth escape velocity, for example, you want to go into a lunar orbit, you get 1 day a year where you can access that orbit. So we aim for a little bit larger, 1 kilometer per second. It's an easy number to shoot for and overcome. This gets us into interplanetary space, and we can improve our access to lunar orbits by 100 days a year. So, our nitrous oxide hybrid rocket might be something new to you. So I want to just briefly introduce hybrid rocket. Hybrid rocket is a chemical propulsion system that's been around where the oxidizer, I don't have a pointer. Okay, this is a liquid oxidizer being injected over a solid fuel. So the separation of the oxidizer and the fuel in different phases makes them the safest chemical propulsion system. Now when we use nitrous oxide and polyethylene as our propellants, we have some nice features. We get 300 seconds of ISP. Our average propellant density is specific gravity of 0.9. And most importantly, nitrous oxide is self-pressurizing. At room temperature, it's 5 megapascals as a liquid. So, as with all chemical propulsion system, we have high acceleration. And in fact, we actually have to be careful not to exceed 3 Gs because we can get such high thrust-to-weight ratios. The nitrous oxide is non-corrosive and non-toxic. Both propellants are widely available commercially, and polyethylene is very easy to manufacture. You can drill it, you can put it in a CNC machine, and create the fuel grain that you need. So, okay, we didn't invent this on our own. Obviously, there's a number of examples, but one that's prominent, this is a picture from the New York Times in February. This is when Beth Moses became the first commercial passenger astronaut. This was on the VSS Unity of Virgin Galactic, and they're using nitrous oxide self-pressurized thruster for their spaceplane. Alright, so like I said, we're using a unique propellant combination that didn't have previous research, so we had to do 2 years of that's me speaking Japanese. And this is a video of basically all of that summarizes all the tests that we did to understand the internal ballistics. Okay, so you can see this test here is giving you about 30 newtons of thrust. So we did a large number of tests at the scale so we can understand our fuel regression rate, our nozzle erosion rate, what the ignition looks like in low pressure conditions, and how to design our injector to eliminate any oscillations. Now we summarized all of those experiments into a MATLAB program, and we most recently put it into the MATLAB app designer, which makes it really easy to run through our iterations and pass on to the students in our laboratory. So what you're seeing here is on the left-hand side, we have our fixed inputs where we define our envelope size and shape, and we explain the constraints that we want to match. For example, nothing can accelerate beyond 3 Gs, or you need 5% of your fuel residual, things like this to stop the calculation. On the right-hand side, we're running parametric analysis. How we design the thrusters, we're trying everything in brute force calculations. So we're setting the range of values for our motor size and dimensions, the inlet and nozzle dimensions, and the supply pressure in the case we're using gaseous oxygen. On the right-hand side, the program kind of spits out a top view and side view of the configuration that you specified in that. Okay, so when we compare our nitrous oxide thruster to the gaseous oxygen thruster being developed, for example, at NASA JPL, here's the results we get. So in our case, we're seeing a slightly larger delta V, and it's mainly because the initial wet mass is a little bit lighter. Well, in this case, a lot of it lighter, so almost 15 kilograms. And because it's lighter, the delta V is larger, despite the fact that with an oxygen system, your ISP is larger. So this can be explained in 2 ways. The reasons it's heavier to use gaseous oxygen in this configuration is one, the storage pressure of oxygen is, in this case, 60 megapascal, and in nitrous oxide it's 5. So your pressure vessels are much heavier. And the second reason is when you use gaseous oxygen, you need less oxidizer in ratio to your fuel mass. So you get a larger fuel grain. And the penalty of having a larger motor in our design was that the motor gets heavier faster than the compression, than the pressure vessels got. So in the end, we seem to have a lighter solution. And so we moved forward with this into our flight model design so we could develop our engineering model to do our final phase of testing. And so here's what it looks like. I'll just point out a few things. It looks like I'm good on time, so I want to point out that one, there's quite a lot of space in between the components that you see here. And one reason for this is we haven't actually chosen the components that we're going to be using for the final flight model. So we spent a lot of time upstairs in the exhibition, admiring the aluminum versus carbon fiber tanks. So this gives us a little bit of leeway to make some more final adjustments before we buy our components. And the other thing is, what you see in the yellow box here, that's essentially a 6U, just to give you an idea of like what kind of space you're working with. So the 6U actually would fit up in the upper compartment where we're going to put everything not associated with the thruster. You can, in this case, if we left it at these dimensions, we would be able to fit payload in between the tanks. For example, a 1U in profile chute where you can eject a CubeSat from the device. All right, so where we are now is we've essentially finished our subscale testing, and we're moving for full duration, full-scale testing. This is a picture from March where we constructed a diffuser type vacuum chamber, and it's now closer to being ready. We're really still working on our thrust mount, so we want 6 degree of freedom of thrust and torque measurement, so we're hanging our motor from compression tension load cells, which is something we haven't done in the past. And so before the end of the year, we'll be operating with this motor down here in this high altitude chamber. And we designed a motor that we could use both a fuel grain that was designed for a gaseous oxygen case and for the nitrous oxide case, just to be 100% sure that our program is giving us the right results, and we shouldn't just skip over the potential of gaseous oxygen for our application. Lastly, I want to leave this word with you. It's maybe something catchy you can remember, the hybrid rocket concept. So we're sharing our ride on existing Earth launch vehicles, and if you're interested in putting your CubeSat into this thruster and going into deep space, you'd be sharing a ride with us. So just keep this in mind to share your ride with the scalable hybrid apogee rocket for space exploration. So let's share a ride. And with that, I'll close my presentation and say that the figures from the paper if you look at it, and if there's anything you have questions about that I didn't show here, I can pull